They just have untold multitudes of old reactor detailed documents, like full designs of pumps, tens of thousands of pages on like hundreds of old reactors. And so the more I kind of like peered into that abyss, the more I was amazed with what was in there and how relevant it was for the problems I was trying to solve in my professional life. And also just how interesting and amazing it was. And it got to a point where I would challenge myself. Like someone said, "Oh, I have an idea about a reactor. Like this is a new type of reactor," and I'd go into Hathy Trust and try to find it with quotes around search terms and stuff. And almost every time I could find at least a paper. And sometimes, like, hey, they built a reactor that was like that. So I was totally blown away with what has been done in the past, and I really enjoy digging into it, and I think there is value for the modern effort. It's not just of historical interest. I think there's a lot that can be sort of relearned and applied or dug up and used for some of the current development efforts.
Just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country,
of course, the world cannot meet it without America.
that is willing to
We're going to need you, the next generation, to finish the
overhaul
job.
nuclear regulation
We need scientists to design new
and
fuels.
focus on net public
We
benefit
need engineers to invent new technologies. We
over absurd levels of radiation
need
protection,
entrepreneurs to sell those
then
technologies.
we will march towards this.
We need workers to operate assembly lines that hum with high-tech,
We
zero-carbon
have
components.
unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
Welcome back to another episode of the Fire to Fission podcast, where we talk about energy-dense fuels and how they can better human lives. I'm joined today by a rock star guest, Nick Touran. Nick is an energy consultant slash founder at What is Nuclear LLC. If you don't know what is nuclear, if you don't know what that is or what is nuclear, just type in whatisnuclear.com, and it's awesome. Nick, I'm really, really stoked to talk to you today.
Thanks, Mark. Yeah, really happy to be here. Thanks for having me.
Yeah. Cool. So yeah, like I said, What is Nuclear? You've got this website that has been around for a long time. You've talked about it a bunch for other folks, but give yourself a plug, man. Like, what's the quick background on this for the ignorant few that may not be aware of?
It started out as just public education. Like I learned about nuclear power, late into my educational career as an undergrad. I was like, nuclear power is really awesome. I didn't know that, and we need to tell the world. And at the time, it was like 2006, and so the thing to do was, well, let's just make a website. So my friends and I checked domains, and like What is Nuclear was available, and so we just grabbed it and we started throwing up like, what's nuclear waste, what's a nuclear reactor, just basic stuff, trying to get it out there, hoping to shift public acceptance and knowledge about nuclear. And so anyway, it was just in the background. It was just a fun thing I did mostly on nights and weekends, out between like regular school and then like an actual job that I got at TerraPower for 16 years. So I worked on it. And it sort of moved on beyond just like the basics. As I got interested in like reactor history or reactor economics, I would like learn stuff and just write it down almost as an exercise. Like for me, you can learn stuff better if you're like writing notes on it. And so it would be like, oh, I should make a What is Nuclear page on radiation on flights or on nuclear economics. And then that would like be an excuse to go kind of dive deep, get some good references, and then throw it up there. So anyway, it just became kind of now it's like a big hodgepodge. It probably needs better navigation. Like there's dozens and dozens of pages and they're kind of all over the place, but it's still fun. And like I get messages from like middle schoolers and from like policy people like who are in charge of stuff. So I get all sorts of, it brings in lots of people who want to talk about the stuff that's on there. So it's been really fun.
That's awesome. It is a tremendous resource in my opinion
thanks.
for the industry. Like, I mean, I know you've been complimenting other like podcasts and shows and stuff, but man, it's been really helpful for me. I think I share the post most often, like you're showing the waste and like the picture of stacked canisters on a football field, and then like actually how tall the actual fission products are.
Yeah. And that was like another one. I like that one. I'm glad that one's helpful. But I was like, I always see, different people say different things. It can fill a football field or can fill a stadium this high or that high. And I was like, well, what's the real answer? So, and I couldn't find like the math anywhere. So I was like, well, I'm just going to write down, my simple math and put the assumptions on there and then just throw it up there so that, I mean, it's not that it's, anyway, so that's like a great example of how those pages come about. It's like,
Yeah.
what's the real answer? I figure it out. I make a page about it.
I love it. I totally agree that like writing, I mean, I love consuming information and taking in podcasts but you get to a point and you're like, well, I've been getting a lot of inputs and no outputs, and I feel like I'm not learning as much as I could if I were putting things out. And so yeah, as a learning tool, it can be really, really helpful too.
Yeah, totally. It's almost like a selfish thing for me.
Yeah.
Yeah.
Cool. We might circle back to what is nuclear, but recommend people go check it out. Your time at TerraPower, you spent a long time there, and you just left this year, like what, 4 months ago?
In March. Yep.
So we'll timestamp this podcast, August 2025, recording it now. Yeah, right.
Yeah, there we go. Yep.
Yeah, talk about your time there and kind of what you learned and
sure.
Yeah.
Yeah, my time at TerraPower was awesome. I mean, it was like such a cool. I went there originally as a consultant. I was a grad student. I went as a consultant in 2008 because they needed someone who could simulate fast reactors with the several software tools that existed to simulate fast neutron reactors at the time. And when they I guess they Googled who's publishing fast reactor results, there just weren't that many. So they called up my research group at University of Michigan and said, hey, come teach us how to run these old Argon codes, which I just happened to know. And so sort of by luck of knowing something extremely esoteric, they reached out to me. So I came out and then I did an internship and then I just never went home. That internship became full-time. They sponsored the finishing of my PhD. The work they needed done there was very similar to what I was working on for my PhD. So they were like, hey, you can work full-time and work on your PhD, which is a great deal, and be in the Seattle area, which was sort of a dream of mine anyway. So it was really a sort of unexpected and awesome thing to get involved in. And it was very small back then. It was I was probably the 9th full-time employee. There were a bunch of consultants, but very exciting. It's
That's
okay,
fantastic.
yeah, we're going to build this reactor. It's revolutionary. We have basically unlimited funding and we're going to build it in several years. And so it's the most exciting thing. And so to work on that every day was so fun. And then, I mean, I think there was everyone sort of grew together, as the institution and the engineers sort of learned more and dug into the details and started doing the detailed analysis. We got into situations where we were like, wait a minute, this thing that some physicist said a couple years ago, is actually impossible when you try to actually engineer it. And so there was a huge amount of just learning and getting smarter and charting a course that would lead to a reasonable reactor product in a reasonable amount of time. And that was a really sort of formative experience, going from we're going to do it in a year to okay, now we have a much more sort of incremental change over the status quo. It's still really cool, but there's a lot of systems, there's a lot of interactions, there's a lot of engineering, a lot of material science that needs to be done and takes time and takes money. And so yeah, building that team and learning all that stuff was extremely was great, and I love that team, and they're now building this first reactor in Wyoming, which is pretty exciting.
Do you have, or can you give a specific example of oh wow, we made a mistake on this one and we have to pivot?
I mean, they if you just look at the publications, you can pull up public publications from 2009, and it was deep underground. It was helium cooled and thorium fueled, and it had no moving parts and was totally autonomous. And then, a couple years later, it's okay, there's fuel management. You can access it. There's maintenance. There's people who go in and move fuel every once in a while, and so you can kind of read between the lines in terms of well, that may be physically possible. The ability to do it right now, have a deep underground, fully autonomous reactor, is just not the first thing that you're going to do. It's not so much that we don't have to say it's a mistake. It's the timing is off. You first have to walk before you can run. And so getting a reactor that gets most of your technology and systems tested out is a prerequisite to getting one that is does something that no one's ever done before, which is run a reactor like autonomously for years and years.
I like that, like path dependency, right? This is like
Yeah.
true innovation is small step changes, not enormous leaps.
Yeah, I mean, I'm sure there are enormous leaps possible as well, but I think it is really hard in nuclear. It's just so much of the space has been so broadly covered by like the smartest people on the planet for so long. And it doesn't mean there's nothing out there that's new. People do come up with new things, but it is extremely challenging, and it shouldn't be your default. Like if you go into nuclear thinking you're going to revolutionize it with your one cool idea, you should be skeptical. Like be skeptical of someone who says that. It'd be cool if they would. I wish them luck, but like it's a lot harder than I originally thought, and it's a lot harder than many
We
people
tried.
thought.
It's hard.
Yeah, exactly.
We spent a lot of money doing it.
Yeah, but there's so many different ways to do things, so it's not like my experience fully covers all possible experiences. But like it definitely like shaped my view of things.
Yeah. It's interesting having real life experiences like that where you're like, wow, our assumptions might have been wrong, and like we learn more and we have to figure out more, and like it kind of forces you to go back and look at history and like examine technology that's already been built before, right?
Yeah.
That's been my experience, at least.
Yeah.
Did
that
you have a
definitely happened to
similar
me.
epiphany? Like you've got this whole hobby of digitizing old videos
Yeah.
labs,
Yeah,
right?
I mean, I'm unhealthily obsessed with like old reactors at this point, and I think that did probably come from this this pathway. It was like, okay, we're gonna solve all these problems, no problem. And then, for work-related reasons, I might be reading an old document about some fuel handling machine that was built in Nebraska on the Hallam reactor, in the early '60s, and like they have solutions and challenges and solutions that are still perfectly relevant to fuel handling in a reactor that you might be trying to build today using the same fluid. So like that's when I was like, wait a minute, there's a whole world of stuff in these archives, and I found some pretty interesting resources. Everyone knows about this one called OSTI, which is like the DOE document repository, but I found another one called HathiTrust, which is like it's kind of the academic side of Google Books, and they just have untold multitudes of old reactor detailed documents, like full designs of pumps, tens of thousands of pages on like hundreds of old reactors. And so the more I kind of like peered into that abyss, the more I was amazed with what was in there and how relevant it was for the problems I was trying to solve in my professional life, and also just how interesting and amazing it was. And it got to a point where I would challenge myself. Like someone said, oh, I have an idea about a reactor, like this is a new type of reactor, and I'd go into HathiTrust and try to find it with quotes around search terms and stuff, and almost every time I could find at least a paper, and sometimes like hey, they built a reactor that was like that. So I was totally blown away with what has been done in the past, and I really enjoy digging into it, and I think there is value for the modern effort. It's not just of historical interest. I think there's a lot that can be sort of relearned and applied or dug up and used for some of the current development efforts. And
I
sorry,
completely agree.
yeah, and yeah, not to say again, it's not that like just because something happened in the past doesn't totally, history rhymes, it doesn't repeat or something like that. Another credit I should give is to Michael Schellenberger, who wrote an article pointing to I can't remember, it must have been 10 years ago by now, but he did an article in Forbes that was about the challenges of operating advanced reactors, and he was referencing a free book that's on the Department of Energy website called Atoms for Peace and War. It's like a 900-page book, extremely well referenced, written by professional historians working for Department of Energy. And I was like, man, where's he getting all this stuff? So I went and I pulled that book up, and reading through that book also was sort of a revelation in terms of just like the depth and breadth of what's been done. And then it pointed to a bunch of things. And lastly, last history tidbit, I for some reason read Alvin Weinberg's autobiography, which is called The First Nuclear Era.
For some reason, because he's
I can't remember like how I heard about it, and I just read it, and it's a very short but like very dense and really excellent book that I recommend to everyone who's sort of even a little bit interested in nuclear enterprise or history. It's a really great book. I think I put like the first Amazon review on it, and now they did a reprinting of it or something, so it's available like only in hardcover or something like that. But very good book, and also really just spoke to me and had so many interesting and useful tidbits that really shaped my view. So that's
Wow.
how I got into that.
Yeah. Awesome. And we could take this in so many different directions.
Yeah.
But I'll have to link to the book on Amazon for the
Mhm.
if folks want to go and check it out. So, yeah, like this idea of learning from the past to build the future, and I like that history rhymes, it doesn't repeat. But like, there's a ton of work that has been done. Like, how does that information get synthesized, and how does it get captured? And like, I mean, you're I'd say like a savant, and from a historian perspective, but also like this combination of being a nuclear nerd and like super intelligent, and, like capable, and like, so how do you put all of these things together? And like, it's easy for you, but then if someone else is trying to do it, like,
Yeah.
man,
Well,
is that part of the
thanks.
effort for like trying to proliferate the information and like capture it on
Yeah.
text?
Yeah. I mean, yeah, thanks for saying that. And I really have leaned into the word amateur for my history stuff. Like amateur, the root of amateur is like amor, like love. You're only doing it because you love it. So like if you're a true amateur, if you really love something, you can like really spend a lot of time enjoying going through it. So I guess I'm kind of on the line of professional now that I am doing more consulting. A lot of people are asking me professionally for like, hey, can you help me find some historical information on this? So
Yeah.
but anyway,
well, like it's easy. You just go look at it and read it, and like just read
yeah,
it. No, like,
yeah, just go
Nick,
to
it's
Happy
not
Trust.
easy for me. I can't do it, so let me pay you.
Yeah, exactly. Well, I think there's a couple things that are happening. Like, I do think so. Right now, the AI chatbots are extremely capable and can do all sorts of amazing things, the large language models. However, when I go into the cutting edge models and ask them about nuclear history or the basis of nuclear things that have happened, they are amazingly wrong, like almost every time. Like they can get some basic stuff, but if you ask them anything even a little bit sophisticated, they just don't have enough material to go on, and so they just aren't that good. And so there's this like moment right now where someone like me who kind of knows this stuff is still, better than the large language models. But I do think that will change rapidly, and I think as more of this stuff gets digitized and consumed by the large language models, I do kind of think that we'll be able to rely much more on them as they get more of that material to sort of say, like, hey, I'm building a whatever beryllium moderated reactor, give me some ideas and tell me some problems and challenges and show me what experiments were done in the past. I think the large language models will make it so much easier than like here I am spending my nights and weekends reading through thousands of pages or at least browsing through them. Having a large language model will make that so much better and so much easier and so much more accessible. So that's one major thing. It's not ready yet, but it's like right on the cusp of being ready. And that's another, like, as I'm digitizing these films, which we were talking about earlier, like I've gotten 45 historical films digitized from the National Archives, and I've been in the more recent ones, I've been running AI on the audio to make a transcript. And then I try to sort of edit the transcript a little bit. Some of them are pretty long, but I try to make sure the transcript, makes sense. And so part of me feels like that's a fun way for normal people, or at least, more normal people to consume nuclear historical information. Like a well-produced documentary from the 60s with this, that same narrator is kind of, some people enjoy. A lot of people on YouTube are like, dude, I just put these on to sleep. Like I just sleep to this. Thanks, man. But yeah, that's just another way. Some people prefer consuming it through video, and then also just digging them out of the archives and get them digitized will feed into the large language models and other AI of the future. So I'm hoping, when AI takes over, maybe they'll have like a credit system where they're like, that guy digitized a bunch of stuff for us, and so we'll be nice to him as the overlords or something like that. That's the real driver.
I mean, yeah, in the present era, there's certainly still value in the human, right? Like, and
Oh yeah, for sure.
being able to synthesize and trust and like double check and
Yeah.
yeah, the technology continues to march forward, but it's certainly not perfect.
Yeah, and I just want to like further emphasize how bad the large language models are. I mean, I get people who are like, "Hey, I asked ChatGPT and it said this, this, and this." I'm like, "Well, that's 100% wrong. Like that's totally wrong." And I mean, I use it all the time. I try to ask it for help digging into things, and it's done recently. It like made up 3 different quotes out of IAEA tech docs, and the quote was like perfect. Like if the document actually said what it said, it would have been like exactly what I was looking for. But when I went to look for the original reference, the original reference didn't even exist. Like there were 3 completely made up tech doc numbers that, and the quotes were completely fabricated. And I was like, okay, well, I
Yeah.
guess I still have to check my original references. But there are people out there who just use ChatGPT and come to a conclusion about a nuclear thing and then talk about it on X. And it's like, now, and they're just so extra confident because ChatGPT said something. And it is like a problem. I've been fighting against like BS in nuclear, even pro-nuclear BS for many years. And like, I feel like it's just getting worse because now the large models are like backing up the BS that they've been trained on. So it's a problem.
Yeah, that is a problem. Actually, my distrust in AI stems from a question about helium turbines. I was like,
Hmm.
find me a helium turbine design that like been used in the past, and like look up patents and look up different
Yeah.
design documents. It's like, oh yeah, here's all the helium turbines and here's the patent numbers. And I was like,
Yeah.
really? I'll go look up the patent number. And it's like there's like a toaster or something,
Yeah, there's
It's like, this
3,
is
right? There's
not
like
correct at all.
Lafleur, Oberhausen 2, and there's one other one I can't remember. But yeah, I recently looked into the same thing, and like those are hard to find.
Yeah.
Yeah.
So why'd you leave TerraPower?
I mean, 16 years is a pretty long time. I
It's kind of
I
weird
was
in the modern era.
Yeah, it's like weird. And again, nothing but good things to say about TerraPower. And like they did, like when I wasn't finishing my PhD because I was too focused on my full-time work, they were like, "No, like you better finish it." Like the CEO like talked to my immediate boss, was like, "Don't give him any more work until he's done with his PhD." They like really pushed me through that, so I owe TerraPower a ton. But yeah, I mean, you can only spend so many years working on the same. It's almost, my joke is that it's like a continuation of my senior design project. Like when I was an undergrad, I did a sodium cooled fast reactor with metal fuel, very similar to the natrium core. I kind of felt like I know a lot about that type of technology. I wasn't learning as much. I mean, it is exciting to be transitioning into the construction phase. That's something that, is like my biggest concern leaving, is like I'm not going to be able to participate as much in like actually doing the construction. But I don't know. I just figured I had just moved across the country for sort of unrelated reasons, for family reasons, and was working remote, and just thought like it was a good time to just see what else is going on in the world and leave on good terms. Like I assume if I wanted, I could go back, although never can be guaranteed. But I just wanted to try something different, see what else was going on, learn something a little bit new.
Yeah, that's awesome. That's I've made similar jumps in the past when I get to the point where I feel like I'm not learning as much as I can anymore. Then that's been a indicator for me of it's time to go. How have you seen, and this might be a super obvious question, but nuclear change over time? Like people are reaching out to you now. Is it more than they were before? It's popular in the news and the press and the investment community now. Like we did it, Nick. It's happening.
It's done.
Cool.
Yes, what is nuclear.com? Will take the win now. Oh yeah, it's changed. I mean, it's gone through many sort of ups and downs. People reaching out now are more on the it's like more investors and institutional people. It's fewer middle schoolers. Like I used to get tons of middle schoolers who would like write in with like homework questions, and that almost never happens now. I don't know if it's because my site, fell down, or they're using AI or whatever. I mean, there was a time when What is Nuclear was like the #1 search result on Google for like nuclear reactor, nuclear waste. And now it's like number 30 or something because I don't know, it's not social media enough. So that may be the only reason there. But and now my audience is more seeing me on whatever, LinkedIn and X. And so they reach out and say like, "Hey, I saw you said this. Can we have a call and talk more about it?" But it's very positive. Like I see very little. Even 10 years ago, there was tons of anti-nuclear sentiment all over the social media. And if I went to a talk when I lived in Seattle and gave a talk on nuclear, people would be like, "Who's paying you?" They would like scream out of the audience. And that just like never happens anymore. People are like, "Okay, so what do we do next to make this happen?" Like it's so much more positive and optimistic. There's very little opposition. That's like one major change. And then the other change is that like the focus of technology has obviously changed. Like in 2006, it was all about large light water reactors in the first renaissance. And now it's all about, the smaller, the better, microreactors being pumped out on a chip fabrication line or something like that. So that's been another interesting technological shift. And in the middle there was thorium, but that's kind of gone down now. So those are numerous changes I've seen.
Nice. I'm optimistic thorium will have a resurgence, but we can talk about that next. You posted about the Dunning-Kruger curve. I might have pronounced
Yeah.
it incorrectly, but what is that? And I mean, this was a question that our producer came up with.
Yeah.
I don't know what this is. You teach me about it.
Yeah, so I mean the Dunning-Kruger curve is this like kind of famous curve where it's a curve of confidence on the y-axis confidence on the y-axis and competence on the x-axis. And so it's this idea that like when you first learn about something, you're very confident in it, and you'll say things very confidently, and then as you become more competent and you get more experience, then your confidence starts dropping way down, and then slowly, as you get really good at it, it starts slowly coming back up. So big peak, and some people call this the peak of Mount Stupid, and then this is like the curve of delivery or something like that. And I put little labels on it to make it nuclear specific, and the labels are from this old 1953 Rickover memo, which we all call the Rickover paper reactor memo, where he says, look, there's two types of reactors. There's paper reactors, which are small and use off-the-shelf parts and multi-purpose and simple and very safe. And then there's like practical reactors, which are heavy and behind schedule and over budget and so on. And so I kind of put those at little points around the curve, just sort of as a commentary. I mean, as part of the resurgence of nuclear, there's a lot of people in nuclear, and a lot of people are very excited about it, and a lot of people are saying things that are almost too excited, and in my opinion, like too optimistic, sort of reminding me of what I was hearing back in the 2009 days. And part of me maybe I should just like let it ride and be like, yeah, go, let's do it, like all the best. But like part of me also is thinking of like, I don't want people to be disappointed. Like I've kind of gone through that curve myself, and it's a little bit hard to sort of realize that, well, like when I this is embarrassing, but I think when I met my wife, like she kind of jokes about this. She was like, so what do you do for a living? I'm like, I'm saving the world, like effectively. And then she's like, what do you do now? And I'm like, I sit in Teams meetings and do spreadsheets. It's like, it's the same thing, but like, it's just a little bit slower and less like, I don't know. And maybe that's just a screw up on my part. Like maybe I should have stayed more focused on directly saving the world. But anyway, the point is, like, when you first come into nuclear, you think everybody does this. They come in, they're like, well, why is nuclear expensive? Well, that's dumb. Let's just do a factory. Or let's just make it small. They have like an easy idea, and they're like, boom, let's go. And you can raise $100 million like no problem right now in this market. You show up and you're like, hey, I've got a reactor idea and it's going to be cheap. Like you will get $100 million almost guaranteed. And then you have to deliver. And when that delivery pipeline starts happening, it gets a lot harder. And so there are engineers who have to sit down and actually make those promises real. And I claim it's going to be a lot harder than a lot of people think right now. And so that curve was just commentary, kind of warning people like, yes, this is going to be awesome, but there's a huge amount of work. There's technology development work that is just really hard and takes time and can be done, should be done, is worth doing, but it's not easy and it's not fast and it's not cheap.
So can you think of maybe, I don't know, some examples, like some low-hanging fruit of different technologies that exist that like people are like, this is going to be easy to do. And it's like, well,
Sure.
there's, I don't know. Well,
Yeah.
let's pick on TRISO. That'll be
Okay. Yeah, I mean, sure. Yeah, I mean, I was going to say thorium for a second. Let's do TRISO first. So, like, TRISO is lots of companies are totally dependent on this TRISO fuel, which is, should I explain? Like, most people know what TRISO is at this point, but I can briefly talk about it.
trispecial isotropic spheres.
Yeah. So
ceramic coating.
Right. It's a very special fuel that instead of just having like a fuel with uranium in it and then a cladding around it, it has uranium in little tiny particles with like many layers of carbon around it, and then those particles are embedded in like a bigger matrix of graphite as well. And so it's a super robust fuel form. It's also like when you look at it's uranium oxide or uranium oxycarbide in there in those little tiny pebbles. And if you look at the actual density of how much uranium is in a pellet of this stuff, it's literally 5%. So there's 20 times less uranium per volume in TRISO fuel. But it has this big advantage where it's really robust and it's difficult to release those fission products. Like graphite doesn't even melt, like it sublimes at high temperature, it cracks, but it like doesn't melt like a metal cladding might melt. You still can release fission products. Like if you go to high temperature, the fission products all kind of migrate out, even though it doesn't melt. But it is pretty robust, and it's hard to come up with an accident where you have like a very large amount of radionuclides released. So people are basically saying, well, if we use this fuel, then our reactor doesn't really need safety systems. It doesn't need a nuclear grade quality assurance program. And so all the capital cost, all the systems and equipment can be from Home Depot, from, a commercial type quality assurance pipeline. You just don't need the level of redundancy or backup systems and diesel generators or any of that stuff because the fuel itself is just so robust. And so that's kind of that's a design philosophy. And people are willing to pay more for the fuel. They're like, yeah, we'll pay more for that fuel. It's much more expensive to fabricate, and it requires, it's like absurdly expensive.
10 times more expensive.
More like 200 times per kilogram to fabricate the fuel right now. Now, it's not fabricated in bulk, and so there's an argument that maybe, even though it's a very intricate and sort of high waste process where you're making these little particles, and they have to be within a certain specification. So what ends up happening is you get a lot of rejects, and so you have to like recycle them back through. But if you've already coated them with carbon, it's like pretty hard to you have to kind of burn the carbon off or crack it off and put it back through the system. So it's low throughput, small batch process. Is very difficult to scale. Lots of people are trying to scale it. There's like 4 or 5 different TRISO fabrication facilities going up right now. A few companies are making it in small batches, which are going to fuel the first TRISO reactors. Like Pele already has fuel fabricated. So yeah, but it's besides being extremely expensive to fabricate, because of that very low uranium density, 5% of uranium oxide, you have to put in a much higher enrichment. So instead of 4 or 5% enriched, you got to put in 15 or 20%. And so now you're spending a big premium at the enrichment plant, and you're mining a lot. You do get more energy out than you would so you go to high enrichment and then you burn a higher fraction of that fuel. So from an overall sustainability point of view, it's like not that different. But from a cost point of view, because of the premium of higher enriched uranium, it's like absurd. So like the fuel cost is, it can be up to $60,000 a kilogram, including enrichment and fab, or even more for some of the early batches. So
for the economics.
Yeah, I mean, when you do the math on it, which I've done in a few tweets, like if you just take the fuel, assume the reactor's free. Let's say the factory process works, and like you just pay nothing at all for all those pumps and sensors and vessels and containments and shield and hundreds of tons of shielding. All of that's free. Well, the fuel alone at a certain reactor size is already 3 times what like natural gas electricity is, a full system. So it doesn't mean it's not a terrible idea. It is like an intriguing fuel. Like that safety benefit is real, and it is cool. And it can go to really high temperature as well. So you can use high temperature gas or high temperature molten salt and do some high temperature thermal processes or whatever. And that's all legitimately cool. But like the fuels are expensive. The systems are low TRL, and like it's definitely worth trying. But it may not work at all, or maybe like way too expensive. It
sounds like the innovation necessary in this circumstance is like fuel needs to be cheaper, right? And like with comparable quality control.
Yeah. Yes, there's plenty of room for innovation in fuel fabrication of that type of fuel, but you still can't really get rid of the fuel enrichment is expensive issue. Like you still need HALEU, which is also like even if you made the fabrication better, it would still be relatively expensive. So, but if you really can just build a dirt cheap, non-safety related reactor, like maybe the cost could be down. But I mean, even then, Like, there is still stuff that has to be in a reactor that has no safety systems. Lots of stuff. You still need the bulk shielding material, which, isn't super expensive, but it's massive. You still need a control, instrumentation and control system. You still need a coolant purification system that's pulling any impurities out of the coolant during operation. You need a leak detection system. You need all these, you need HVAC. You need a bunch of stuff that costs money. And that's where, the bigger reactors have the economy of scale advantage. So,
or you might only have those systems rather than an independent system.
yeah, I think certainly like large high temperature gas reactors are like totally reasonable for a thing that might work great. But I think that like micro HCGRs, I really don't see the case. Like I get in trouble for saying this too much, but like I don't see a case outside of high electricity, high power cost fringe type uses. So they're perfect for military bases like Pele or remote, anything remote where they want to pay a premium for that type of awesome capability. It's perfect. Like it's an awesome technology and it'll be great for that. But when you're talking about powering a home in Chicago, competing with the bigger reactors in natural gas, like that's where I think the story gets a little bit lost. But again, I shouldn't worry about that too much. If someone made a sweet micro HCGR that made power in a remote area, that would be like the coolest thing ever, and I would be all over it. And just because they thought maybe they could get costs down but didn't, that's not so bad. Like that got them funded to do the development, and they made a useful product for a small group of people. It doesn't save the world, but it's still a really awesome use of nuclear. So that's kind of where
absolutely. I guess I'm optimistic on like where there is technological innovation and like step change opportunities, like people can step in and start businesses to solve those problems. So like we're calling out, hey, the fabrication cost for TRISO is expensive. And like BWT manufactures has been, they like to tout that they've been manufacturing it for decades, but like it's still expensive. There's surely, I struggle when people say like, well, we're the incumbents and we're the experts. Like there's, I think often opportunities for people to come and be like, well, let's look at like how to actually do this a little cheaper and maybe a little better. I saw it like similar technology, but like with frac sand and frac ceramics and the upstream oil and gas industry. Like we got better and better at finding cheaper and cheaper solutions, and it was like a little step change. I mean, we started using just dirt out of the ground instead of like high quality ceramics. So not a perfect analogy, but like there were companies that had innovative ceramics and technologies, and they came in and made them cheaper and cheaper. So.
There is a great opportunity to try to make cheap TRISO fuel, and that would be an enabling tech for a lot of reactors. And there are, like Standard Nuclear just got the IP from Ultrasafe Nuclear, who had a pretty cool modular, scalable TRISO fabrication technology going, and they are going to start, trying to build that out. X Energy has one. A couple other people have TRISO fab. So it's a great opportunity, and there's no law of physics that says TRISO fuel fabrication will always be expensive. So I think it is an opportunity, and it's a cool thing to work on. And then like as with any advanced technology, like we have run TRISO fueled, high temperature gas cooled, helium cooled reactors before, right? Like Fort
one in Colorado. For the thing,
which is famous for being extremely touchy and never running. And there's a great headline in the New York Times.
Have you been inside?
No, I've never been in. Have you been in?
Dude, you got to go check it out. Like we got a tour of it, and it is like a horrendous design for operations. Like you can imagine like a nuclear reactor, giant concrete slab, like the shielding that was in place. And then like all of the helium pumps they put around the whole system, they're just like spread out all over the place, and they leaked. And like we talked to one of the operators that was there, and like it was hot to work on, and the NRC was looking over his shoulder all the time. And he's like, yeah, no, I worked here for like 5-10 years, and eventually I just got fed up and like went down to Pueblo and worked at the coal plant. And I was like, why? Because the NRC wasn't looking over my shoulder, and I could just do stuff.
Like, they had tons of I mean, there was a major design flaw, which was that they had like a water cooled bearings and seals on the helium circulator, and the water kept shooting into the reactor, which is bad. If you get water in a hot graphite reactor, the graphite oxidizes, and you have like big issues. Oxidizing graphite, no good. And so the headline was world's safest reactor shutting down because it never runs. That was the 1980s headline when it shut down. So, and it wasn't, and so like the fuel alone, TRISO doesn't like solve the nuclear challenges. And that reactor was, I mean, it well conceived. It had a few problems. Like you can just not put water cooled seals, and that would get rid of the major issue for that reactor. But it just kind of goes to show that, well, we just have to have to rebuild a rich exploratory environment that's hands-on with different types of reactors. And so that is something I am very happy right now to see. And it's best to do that with very small prototype scale reactors. And so like now there's 10 different companies that are going to try to go critical in a year. And like, okay, they don't have any
yesterday.
Oh yeah. I thought two aren't two like both Oklo. Yeah.
Oh yeah. Yeah, I guess, yeah, maybe.
But like that's, I mean, a year is if you're gonna take engineering shortcuts and just slap some crap together, like it's better than nothing. Going critical is gonna be cool no matter what. But
I guess for folks that are unfamiliar, like what are we referencing? You and I.
Yeah, the Department of Energy related to one of the executive orders. There's a goal to get 3 new nuclear reactors, Gen 4 type reactors, critical outside of Department of Energy sites by 4th of July 2026, which is in 10 months. And so they just, everyone who wanted to sort of get that fast track applied, and it was just announced yesterday that like these 10 or 11 companies are all like approved for fast tracking, so off you go. And so everyone's going to be scrambling to try to get anything critical by that time. And conceptually it should be doable. We have enriched uranium now, like assembling a stack of graphite and uranium will go critical. Like, is it going to be a good high performance reactor? Almost certainly not. But
this is like a massive, I think it's a massive step change for the industry. Like, yeah, because to get to this point without this authorization was at least a 3.5-year licensing period from the NRC. Like, what was?
Yeah, I mean, I will say, yes, it's the urgency is super exciting, is really needed, and I'm happy to see it. So, like, for sure, it's a good thing. I will say that, like, a lot of the stuff that goes on during licensing process is legitimate engineering design. Like, a lot of times the license asks questions that you really should know the answer to perform an appropriate engineering analysis. So it's not the license. I mean, so doing like 3 years to go critical for like a new type of reactor that you're just starting conceptual design on is pretty aggressive. Even back in the 60s when people started or working on very fancy gas-cooled beryllium moderated reactors like the EBOR, it was a 3-year design period where they had dozens and dozens of people performing elaborate analysis of the stresses and strains and thermal strains in the vessel, what happens when it turns on and turns off, and making sure they had systems in place to do that. And so if you say like, okay, go critical in a year, you don't have time to do all the transient analysis, so you cannot assess what's going to happen to your reactor under all conditions. And like, even if there were no regulations at all, you still want to know what your reactor does when you turn it on or turn it off. And so there are some things that for a typical power plant should take a little bit longer than that. But like, we've been sitting around doing studies for so long and not going critical for so long that I totally agree that like, let's just go critical. It doesn't have to be the world's best reactor. Like, it will lead to the world's best reactor like the next time. Yeah, and so just getting that sense of urgency.
Those models are all dependent, like any model is dependent on the inputs and assumptions that you have.
Yeah, exactly. And so let's get back
the bounding conditions that you use, and like just from turning it on, you're gonna have so much more data available to update your models and make
for sure.
Like, I think like the design, build, iterate, like do loop, it should be used more often in nuclear. And like, that's been really, in my opinion, prohibitive for the industry to like build anything new. It's like you can't actually go build something and test it. You can make all the models you want, but so anyway,
it's really true, and it like further emphasizes why this is important. And there's a whole class of skills that are completely lost. It's like the hands-on sort of the plumbing, high temperature plumbing. One of my friends, Brian Kelleher, did a great article in Nuclear News a couple months ago about high temperature plumbing, and like, just getting a flange that can carry molten salt or liquid metal at high temperature and doesn't leak and can be maintained is like a hard skill. And you can run all the simulations you want or read all the old books you want. Unless you're sitting there hands-on with the hardware doing that, like you will not really learn that. And we've lost generations of people who have those skills. And so this kind of project, we're getting the hands-on experience with the high temperature fluids, with the actual neutrons, with the actual fission products, is probably the fastest and best way to really relearn the stuff that you really need to know. And then that'll feed into the design process for the more commercial product side of things. So it's really great in that it's going to like build this whole new generation of people who are like playing with reactors, literally like hands-on. And so it's extremely exciting, and I'm
totally, man.
really glad
It's
they're
like
all on there.
the Forza Brain's a good example of where, I mean, they built a smaller system, like I think as a prototype, and then like
Peach
scaled it
bottom.
up.
It was a big prototype.
Yeah, small prototype, right? But like this operating experience with real systems, that there's no supplement for it, in my opinion.
Right.
And like your example of molten salt flange is a good one, but like even in well understood industrial technology, like stuff still breaks and there's maintenance. Like operating matters. So
right. And yeah, like, hey, my control rod drive just broke. Like, can you go look at it and fix it? Like that's a hard skill. And so having people who can go like, oh, sure, let me go fix that control rod drive mechanism. And like, I know what I'm doing and I've seen this before. Like that's a essential type of person who we just don't have too many of right now. And so having 10 or 11 companies all having people physically building control rod drives it'll be great. There's nothing negative about it.
Yeah. I guess like we might share the caution for the world that like these things, not all of them are going to work, and there's going to be learnings and it's going to be expensive, but like this is a positive step forward for the industry.
Yes.
Of the 10 or 11, do you have a bet on how many we're going to see that actually go critical between now and?
I think like I'm gonna say like 4 are gonna actually go critical. I believe that 4 can do it, and the only way that I think they can do it is to basically just build the core, maybe like a vessel with a core in it. It'll be hard, and then basically do what we'd call a critical test or a low power or zero power critical test, where you've got the core, maybe it's in a vessel and it has some control rod drives, and you're gonna pull those drives out, and that thing's gonna go critical at basically 0 power. So it's not gonna make a lot of heat, but you'll start learning about the characteristics of the core, see how it changes if it heats up and cools down. It's a typical step in the commissioning of reactors to do these critical tests. I think as that's happening, other people will be slapping on coolant pipes and putting in circulators and pumps and building the rest of the system that's necessary. Like I think otherwise there's just no way you can meet that timeline. But if you just focus on slapping together a core with control rods and going critical and sort of get a conditional license that's like you can't come to power until you do more transient analysis, but you can go critical, I think I'd say there's enough excitement and funding and capability and fuel to do like at least 4. So
I'm gonna bet 6.
Nice.
What do you think? $100? Like 4 or fewer and you win, 6 or more and I win, and 5 we tie. Like,
I don't know, like 4 or 6 is kind of like it's all. I feel like it's plausible. Like going critical shouldn't be hard. Like it should be embarrassing to like worry about going critical, but there is like fuel supply challenges. There's only so much of this TRISO that you can get. But like some of these guys are just using uranium oxide, which you can go down the street and buy, and like putting that in a core and going critical. Yeah, we'll see what the fast track is. Like how much do you have to make sure that your reactor doesn't explode when you turn it on, like that, like how much transient analysis is going to be required? I don't know. Like there are plenty of reactors that you can design a reactor that's totally unstable. It usually doesn't just go critical and then immediately blow up. Like we've done this before. The Canadians built 2 reactors, the Maple reactors, that were inherently unstable, totally against what they expected. But you see it when you do the low power ascent to power, and they're like, whoa, and you put the rods back in and you're like, yikes. And they canceled those, got torn down. They lost hundreds of millions of dollars. But so are we going to just not worry about it and say like, sure, it's your money. If you build a reactor that's unstable, your problem, but like you just can't come up above.
I don't think that DOE,
power.
DOE is not funding any of it, right? It's the
they're just fast track. The DOE, if it's off site,
you have permission to build.
Who's licensing them? Like that's the thing I'm not totally sure. Like whose authority?
I think it's the DOE. I don't know. They found like a mechanism to do it.
So it's DOE, but not on DOE sites.
Yes.
Yeah. Anyway, there are like it's the SL1 reactor, and this isn't, I don't mean to be like too whatever cautionary, but like SL1 was a tiny microreactor, right? It was like 250 kilowatts, and it didn't, when they pulled the rods out of that, some guy pulled a rod out and it killed 3 people who were working on the plant. These are dangerous machines.
Potentially only murder suicide.
Yes, it could have been hypothesized to be a murder suicide from a love triangle, but not confirmed. But like they're somewhat dangerous, or they're hazardous machines. Like a little tiny reactor isn't going to cause a wide scale radiological incident. It just doesn't have enough fission products in it. But it still can be, dangerous to the people working on it. So I think, and as far as I can tell, people are still respecting nuclear safety culture and all that stuff. So I assume it'll go fine.
Yeah. I'm excited for it. I'll take the bet if you take the bet, Nick. But 6 for me.
Well, let's do $10. I'll do $10.
All right.
Over under.
That's fine. Yeah. High confidence.
You can see how my consulting business is going.
So, let's pivot to fuel. We talked about TRISO. We talked about enrichment. Something that I think is underappreciated, and I'm curious about your opinion on this, is conversion. I don't think have you looked much into the conversion supply chain?
Not too much. Like, I'm not a conversion savant like some other people on the rotation, but like, yeah, it's a serious constraint, and we have basically wiped out our ability to do any uranium conversion. Yeah. And there's a bunch of like similar supply or fuel cycle capabilities that we've sort of abandoned, which I'm pretty upset about, and is not like good for like fabricating MOX fuel, which is mixed oxide. It has uranium and plutonium. There's this story where we have a couple tens of tons of separated plutonium from the weapons program that we would like to downblend, mix with uranium, and then put in our power plants. It's sort of a swords to plowshares type of program, where instead of fabricating it into bombs, you put it into power plants and you power cities and power people's lives, and it's a beautiful thing. Well, to do that, you have to be able to fabricate fuel that has both plutonium and uranium in it. And so we said, okay, let's do it. And we started building a MOX fabrication plant.
Where was that?
In South Carolina. And for some reason, I don't know exactly why, but it boondoggled out of control. We spent $8 billion on it. It wasn't even half designed or anything like that. This lesson of like, finish the design before you start construction. They hadn't learned that lesson even on that plant. And so we ended up just canceling it. There was a bunch of corruption and all sorts of stuff. And so it's like, we can't even build a simple fuel fabrication plant that has, plutonium's more radioactive than uranium. And natural enriched uranium is like barely radioactive. You can hold it with a glove, whereas plutonium has some more alpha particles coming out. So it's like a little bit radioactive. So you have some more extra precautions, but like, we can't even build that facility. And so what kind of a nuclear country are we? That's like, people talk about reprocessing the waste and refabricating stuff with like really hot fuel. This is like pretty clean plutonium. Making a reprocessing plant is way harder than that, but we can't even do a MOX plant. And so I was very disappointed in that. And I sort of somehow wished, I don't know, if we had saved it or like done the project management better and actually built the thing. And now, so then the plutonium was going to be just disposed of, like buried. In these executive orders, they said like, oh wait, don't bury that plutonium. Let's hang on and see if we can do something else with it. So I was very happy to see that. So the plutonium is still around, but like, we can't even make fuel with it. So, and then
what steps would we have to take to go and do that?
It's basically restart that project, or like, do an analysis, or like send in a guy give him a 1 week, review the project and find out why it failed. People have tried this, and I'm sure there's some lessons learned, but then I don't know, like put better people on it, better project managers, find someone who can actually deliver on an industrial facility. Like, I don't really know exactly what that entails, but like, just commit to it and do it. And, make the project better aligned with success or something like that. There's a bunch of studies about how do we fix nuclear construction of power plants, and I assume the lessons would be similar. It's like, make sure the contractors get more money if they deliver. Like, if you make it a situation where like you can just keep on doing changes and they just keep paying you, then you're motivated to just keep being slow. Like, you're just collecting money. So make it so, align it so that if you don't finish it on time, like, you start losing money, and find out if that's a contract structure that can actually be possible, and then just somehow facilitate its completion. And similar things for there is a lot of movement in enrichment space. I mean, we see this new company, General Matter, which is cool. And
Centrus off the charts. Like,
yeah. This
the
is
financial performance of that stock is just unbelievable.
it's awesome.
Yeah.
That's a good
My buddies
sign.
bought in, and I did not, and I was like,
sorry.
oh my
Yeah,
God.
I always try to like invest outside of nuclear because I feel like I'm personally
too
already
much.
so
Every
invested.
time
No, I'm just too like I'm
When I
already.
sold my new scale stock when Carbon Free Power Project was ended. Yeah, and
Yeah.
that was the exact time to buy.
Yeah, that was definitely the time to buy. That's a bummer. Anyway, but yeah, so conversion is another thing that, we kind of shut it all down. We had all sorts of enrichment, conversion. We had reprocessing. I mean, the Atomic Energy Commission would reprocess fuel from every reactor. Like you'd burn your fuel for a while, send it back to the Atomic Energy Commission. They'd reprocess it, refabricate it, send you new fuel. They charge you for how many atoms you split. It was like a leasing type of deal. Like you never actually owned the fuel in the really early days. But now we don't reprocess at all. We don't do conversion. We don't do that much enrichment. I am glad to see movement in the space. There's a lot more people and excitement, but a big part of this, you probably know the story, was the START treaty, where we started buying downblended highly enriched uranium from Russia in the early 90s after the collapse.
To megawatts.
Yes,
Right.
exactly. Yeah. That provided half of our enriched uranium need for our whole fleet. So it was powering 10% of the United States' electricity came from dismantled Soviet nuclear weapons, which is really cool. But if you're in the conversion industry or the enrichment industry, it does kind of throw that off a little bit.
So, I mean, we talked about opportunities. I call them opportunities in the fuel space, right? Like every problem can be viewed as a challenge or as a predicament or an opportunity.
Yeah.
I mean, I think there's huge upside for a lot of people trying to get into the industry now. Like, I mean, that another benefit of kind of these 11 reactors coming to market and like all of the advanced reactors and, the nuclear companies saying we're going to build a fleet model and like, that's putting stress on the fuel supply chain, right? Which is both good and bad. It's bad because there could be bottlenecks and long lead times, but it's good because like there hasn't been a financial case to be able to underwrite a lot of these new facilities. Like if any additional capacity is desired in the market and wants to be built, it has to be underwritten somehow, right?
Yeah. Right.
Are there other areas that you see in the industry that could fill that niche, or that I guess that could become available as additional reactors come into play and are built?
Well, you mentioned helium turbines.
Helium turbines, right?
Yeah. There's a whole world of
Dear
like
Siemens, please build helium turbine.
Yeah. Let's do this again. Or and there's another.
Again, I'd say more about that, but I can't comment on it.
Okay. Yeah, I mean, if we do start making high temperature reactors that are easy to maintain and operate well, there will be pressure to transition the power cycle from the traditional steam ranking steam turbines over to Brayton cycle gas turbine type stuff. So you can do helium turbines, you can do nitrogen gas turbines like we did at ML1, or you can even do supercritical CO2, which is another thing that's been like perennially in development, and it's going to revolutionize everything soon, but like it's been kind of slower than people expected. But it has major advantages if it works, where you have better thermal efficiency, more compact turbo machinery and stuff like that. So there's a whole world of supply chain where like nobody's making stuff like that. And if we get lots of microreactors coming along, like maybe a lot of them want to vertically integrate. Maybe they'll make supercritical CO2 turbo machinery as well. But also maybe that's another place where like a supply chain could really ramp up. That's kind of an easy to separate.
Or they have one division that makes a turbine, and then that division spins off and gets sold and just makes turbines for all the other.
Yep. And it's all the reactor components for all the advanced reactors. Like if any of these advanced reactors take off, there's a whole class of components that need to be fabricated in mass in order for that fleet to take off. So you can imagine molten salt pumps that work in high radiation and don't leak, heat exchangers, compact heat exchangers, printed circuit heat exchangers, would be very beneficial to all advanced reactors, like the sodium liquid metal cooled could really benefit from that. And all sorts of auxiliary systems. There's a whole industry that could like ramp back up that we kind of used to have, where people make a sodium liquid metal purification system. Like you can see ads for this in old nucleonics magazines from the 60s, and like we have to get back to that, where you can like open up the magazine and it's like, here's your flow sensor, or here's your electromagnetic pump for a liquid metal. Like those are all things that,
Instagram ads, right?
yeah, exactly. It should be
ChatGPT will
Instagram
be
ads now.
referring you to the companies.
Yeah, it'll be like voiceover on viral TikToks. Come on down and get your printed circuit heat exchanger.
Molten salt circulating pumps, right?
Yeah, I mean there's a whole world of supply chain. Like none of those things are being fabricated, even for for other purposes. Well, the compact heat exchangers are, but for these particular fluids and temperature regimes, those are like specialized with special code cases. So I think there's a whole world that would take off if we can get any of these advanced reactors with different fluids up and running in a case that actually looks good, and someone actually starts making orders of them because they look that good.
Yeah. Awesome. Nick, you've spent a lot of time thinking backwards about the industry, and not backwards, but looking back on the industry and looking at the history, and you've worked on developing new systems yourself. You've done a lot of the math, and yeah, we just talked a little bit about what's next in the future, which is awesome. But leave us on an optimistic note. What does it look like in the next 5-10 years, and what are you going to do to help? Like, what's your role going to be?
Well, yeah. So part of like leaving TerraPower, I intended to spend like 6 months to a year surveying things and figuring things out, and then like making a decision about what to like really dedicate myself to. And I'm only a few months out, so I have yet to determine exactly what I will personally do. But I do think that, yeah, there is more momentum now than we've seen, at least since the first nuclear renaissance in nuclear. And I really think this time it feels a little bit better. It feels like there's more priority, more support, and a lot more private investment, and a much richer variety of different technologies that are being developed. And I do believe that, if you put your mind to it, you can accomplish anything. There's nothing that prevents these advanced reactors from being, someone can put in the elbow grease and get that thing running in a way that is actually maintainable and operable and reliable, and that could be a great product. And so I do think we'll see at least a few of these advanced reactors take off. Meanwhile, I think there's also more and more interest in just accepting that like the light water reactor is a highly optimized, very well designed system with decades of experience baked into it, American ingenuity encoded on its blueprints. And taking the experience we had at Vogel and learning from it and building 10 and then 30 more big light water reactors is like another thing that I truly believe has to happen and will happen. So I want to see like 30 big reactors and 300 small reactors in this country in the next 25 years or something like that. I think it's possible. I think there's like the momentum, and I think if we at least sit down and focus on it, don't kid ourselves, then that kind of thing should be possible. And I want to be a part of that.
For hire, right? Smart brain for hire. So
yeah.
Nice. Well, Nick Touran, thanks so much for the time. It's been a joy chatting with you.
Yeah, of course. It was great fun, Mark. Thanks for having me on.